Hello everyone, my name is Karina. Our group has been engaged to calculate the value of a 1 year's put options for the AFIN270 Composite Index with an exercise price of 4,750 that is purchased on the 1st of September 2015. Now we are going to present individually in order to perform our calculations. First of all, as we can see in the AXX graph, the AXX200 index has dropped dramatically in 2011, and index has continuously increased from 2012. On 8th of August 2011, the Australian Security Exchange saw nearly 35 billion of shares value loss, with a plunge of 2.9% as panicked investors led share price down into bear market territory, pressuring investors of high exposure to dump shares in favor of margin call. Furthermore, in 2013, it is a dumper year for stock market return. In a boost workers' superannuation savings, the stock market's keys ASX 100 index increased 15.1% this year to 5,352.2 after ending the final sessions of trading today down to 46 points. For the next questions, there are two types of options, call options and put options. Call options provides the holders the right to buy security. Put options, on the other hand, provide the holders the right to sell a security. A put option allows the holders to sell an underlying asset at the exercise price, so their payoff is maximum X minus ST zeros if in the future X is larger than ST. In our topic, we'll focus on put options only. The values of stock options can be broken down into two components called intrinsic values and time values. Intrinsic value is the difference between the value of the stock and the exercise price, our price at which the stock can be purchased by the holders of the options. Based on the analysis we've just mentioned above, we can use the Monte Carlo simulations options models can be used to calculate the values of an options with multi-source of uncertainty or with complicated features. The technique applied then is, first, to generate a large number of possible but random price paths for the underlying via simulations, to then calculate the associated payoff of the options for each path. Then these payoffs are then average discounted to today. So now I'm going to pass to Anatole to present question C.
So I'm going to do question C, and I was asked to provide a suitable parameter estimate and perform the Monte Carlo simulation, and explaining why we chose to perform the number of simulations that we have selected. So first of all, the parameter estimates that we needed to estimate the Monte Carlo simulation include the risk-free rate, which was found on the RBA website, and we took the 1 year zero coupon rate from the RBA website, and so it can be seen in case B6, it's 2.65% per annum, and then we used the Z table with a probability of 0.05%, and we found a Z score of 2.575. So we used this Z score since we want a confidence level of 99%. And then to do the simulations, we needed the mean price of the index, of the ASX 200 index. And so we just did the average of the column G in simulation, in price, so here. And we found the mean price of 4,989. And similarly, we needed the standard deviation of price. So in the same way, we just do the standard deviation of the J column. And we found a standard deviation of 569.16. And so now we have all the parameters needed to perform the Monte Carlo simulation. And so before starting the simulation, we should estimate the number of simulations needed in this model. And so it's known that when we increase the number of simulation by n, it will decrease the standard errors by 1 divided by the square root of n. And so in this model, we want the number of simulation to be such that we are 99% confident that the expected value of the put option will be accurate to 1%. So in other words, we want the range of the confidence interval to be 1% away from the expected value. And so the formula for the number of simulation, which is n, is the standard deviation of price, so 569, times the z-score, 2.575, divided by the mean price, times the probability from the z-table, so times 0.005. And all of this squared. And so you can see the formula here, J3 times J4 divided by J2 times 0.005 to the squared. And so we found the number of simulations to be 3,451.
Hello, I'm Howard. Thanks for the anecdotal talk about how to choose and use the parameter estimate. At this question, I'm going to talk about how to calculate the value of the put option. First, we calculate the daily return, use the risk-free rate and the volatility and the z-score. And the z-score is use the random number. Assume the normal distribution is the range is the 0 to 1, and the random number is the between the 0 to 1. And we use the law means inverse function. The normal random number, such as the probability, get the z-score like here. And we calculate the daily return based on this formula and get the daily return, and then we use the data price to calculate times to the each and the daily return, get the let's say the asset price. When we expect the asset price at the end of this 1 year, we got the put current price is the for example is the 4,961, and the exercise price is 4,750, and we use the exercise price minus the current price is the negative result. So the payoff is the 0. And then we go to the simulation because we have to simulate the more than 3,451. So we don't want to manually to do this one. So we use the macro function. First, we use the recall macro at the view function, and we can rename the macro like this one, simulation, and then use the shortcut key is like this. And then the macro function is starting record the order on the computer. So you can insert, then shift the cells down and go back to the option model, copy the payoff to the simulation, the payoff column. And then the order in the macro is not good enough because we want to we want to simulate the 3,451 times, so we have to edit the code, edit view mark code, and editing. And in here is the Visual Basic Editor. So we have to code it at the time series, and based on this code, the computer would simulate the 3,451 times by the order. So when we finish the code, we go back to here, use the shortcut key, and then the computer would automatically to the simulate the result at the payoff. So we have to wait for the few minutes to wait for the computer finish the simulation.
Thank you, Howard, for calculating the put option price and explaining the procedures. My name is Bowie, and I'm gonna answer the question E. According to Howard's calculation, we've got the number of required stimulation for the put option price, which is 3,451. So we use this for 3,400 stimulation to process, and the result is as the list in the left hand side, which is here. We got 3,000. We got all the figures here, and this is the graph for our result. So the mean of our result is 92.36, which is the option price should be $92.36. The standard deviation is 218. The large standard deviation is because of the higher amount of result is located in the negative area. Because the price can't be negative, so we assume all the price becomes 0. That's why we've got a large standard deviation. The standard error is because of is related to the standard deviation and number of stimulation. Also, if we sort the data by ascending, we can clearly see the distribution of the result. We've got more than 2,500 of result is at the negative area. Next, the skewness is 2.5 and the skewness is close to 8. This the skewness highest amount of skewness result the distribution become very sharp, and we've got two tails at the side.
Okay, thank you for Boris' present. Now I'm going to compare the particular simulation and the black square model. The black square model is one method to calculate the price of options. When we're talking about the option price, there are 5 factors. The underlying price, store price, the exercise price for that option, the time to expiration, the volatility of the underlying stock, and the risk-free rate of interest that are going to go into the black scholar option price model. So we are going to talk all the 5 factors and use the black scholar show some price model figure out what the option is was where to start with view of put options. Now here is the formula for the put options. The model is including 2 parts. Here is the first part, provide the calculate a correct view of paying the exercise price up expressions. This is second part. This part of this formula shows expert benefit of purchasing the outright. In our example, exercise price is 4,715 and time is 1 year. Risk-free rate is 2.65%. Volatility is 30.95%. We calculate D1 equals 0.8146% and D2 equals 0.6751 using the D1 and the D2 formula. You can say the formula either. And using the Black Scholar formula, we got the option price is 97.2766453. The multicolor has been used the price standard options. This is an example average. In our model, the sample average of our simulation is 92.36 with around 3,451 simulations, which is the price of our two option. The difference between this result we got from the Black Scholar 97.27 minus 92.36, which equals 4.9136. And if we change the simulation to 5,000, we can say the results change it to the 92.99. The difference is 4.28. By comparing multicolor simulation and the Black Scholar model, we can tell quite easily that the error gets smaller as the number of simulations increase. Okay, here's of our presentation. Thank you for listening.